Hello. Today we're gonna discuss the order properties of the real numbers. These properties basically are about positivity and inequalities between elements in the set of real numbers. Again, the general approach is that we're gonna start with some axioms and properties, then using these axioms and properties, we deduce other theorems about the set of real numbers. The order axiom says the following: there is a there is a non-empty set denoted by P, which is a subset of the set of real numbers that satisfies several properties. So P here is an abstract subset of the set of abstract real numbers. But for intuition, the thing about P here is the set of positive concrete real numbers. The axioms say the following: if A, B are elements in P, then its summation A plus B is also in P. Similarly, if AB is in P, then its multiplication A multiplies with B is also in P. If A is an element in the set of real number, then either A is an element in P or A equal to 0 or minus A must be an element in P. And P here again equals the set of positive real numbers. So what is so important about the axioms? The point is that this is the minimum set of properties such that we can deduce all regular usual properties for ordering real numbers. By obtaining such a minimal set of properties, we can apply this theory to many situations when you only had to verify these axioms. Now let's see how we can deduce other usual properties of ordering of real numbers from this set of order axioms. We start with a definition. A minus B is an element in the set P, then in that case, we say that A here is greater than B. If A minus B is an element in the union of this set of positive numbers and the set of element 0, then we say that A greater than or equal to B, or B smaller than or equal to A. The first statement is that 1 is an element in the set of positive numbers. This seems like an obvious statement, but remember, here we start everything from scratch. We only have a finite number of axioms to work with, not the concrete real numbers that you're familiar with. We started the theory from scratch with the minimum number of axioms, and we deduce other properties using these axioms. So how do we prove this statement? Again, we had to use the order axioms here. And the third one will be useful. The third one says that for any real number, then either this number must belong to the set of positive numbers, or it must be equal to 0, or minus this number belongs to the set of real numbers. So in this case, obviously, because 1 is not equal to element 0, so by O3, the third order axiom, either 1 belongs to the set of positive numbers, or minus 1 belongs to a set of positive numbers. If 1 is an element in this set, then we are done. In the other case, if minus 1 is an element in this set, then by the second statement, second axiom here, you multiply minus 1 with itself. By the second statement, the multiplication of two elements inside the set P gives another element inside the set P. So here, when you multiply minus 1 with itself, you take the multiplication of two elements inside the set P. So the product here must belong to the set of positive numbers. But the product of minus 1 with itself is exactly equal to 1, which is a contradiction, because only 1 or minus 1 belongs to the set of positive numbers. Here, both minus 1 and 1 belong to this set. That's why it is a contradiction. That's why this case doesn't happen. So we're done with our proof. Now, I'm going to say a few more theorems about the ordering properties of real numbers. There are quite a few statements here. The key point to remember is that these statements actually just formalize the usual behavior of ordering real numbers that you're familiar with. The reason they are called theorem is because we started the theory from scratch with only a few axioms. That's why we had to reprove these usual properties. For example, for the next term here, part B say that if A is greater than B, then the conclusion is that A plus C is greater than B plus C. This is obvious from our intuition, but remember, in this case, we had to deduce it from the set of axioms and properties we learned earlier. Another term here say the following: if A is a real number and A is not equal to the 0 element, then in this case, A squared, which is the product of A with itself, must be greater than 0. In other words, it is a positive number. Also, 1 is greater than 0. And more generally, for any number, for any integer n, it is greater than 0. A step further in the theory is that we can use the Bayesian along with the theorems we deduced earlier to obtain even more statements. And one line of important statements is about the derivation of inequality. Here, I'm giving you an example about the arithmetic geometric mean inequality, which say that for A, B is smaller than equal to the sum of A and B squared for any number A and B in the set of real numbers. How do we prove it? We use algebraic manipulation to rewrite A plus B squared minus 4AB equal to A squared plus B squared plus 2AB minus 4AB. Then by simplification, this is equal to A squared plus B squared minus 2AB, which is equal to A minus B squared, which is greater than or equal to 0. By the part A of the theorem we just stated earlier, then the expression A minus B squared here must be greater than or equal to 0. That's why, by the definition above, this one, when you have the difference between two numbers is a positive number, then we say that A is greater than B. So in this case, because we include the possibility of being equal to 0, we say that A plus B squared greater than or equal to 4AB.